Hi everyone, welcome back to the channel. So today we are going to start that bandgap reference circuit, and this is the introduction video. So if you look at any analog circuit, it always look for some precise voltage and current source, and most of the time these are DC quantities and certain properties that it also demand, like these sources should be very less dependent on supply and process, and there should be very well defined temperature behavior. Now, what does mean by well-defined temperature behavior? In most of the cases, we want these three kind of behavior. That is something called p-type behavior, that is proportional to absolute temperature, a constant GM behavior, or a temperature independence, means no dependency of temperature. Okay. Also, we can have something called CTAT behavior. CTAT means complementary to absolute temperature. Means as your temperature increases, the parameter or the voltage or current actually decreases. That is called the CTAT behavior. For example, if you consider BJT, and in y-axis if you have the VBA voltage and x-axis it is temperature, then the plot will look like this. As the temperature increases, your VBA voltage falls, and it has a slope like minus 2.5 millivolt per degree Celsius. Alright, now let us focus on this supply. What does mean by supply independent, or a source which has very less dependency on supply voltage? So we all are very familiar with these circuits. This is called a current mirror circuit. So in this case we have a IREF, and we assume is a golden current source. Means this current source is very constant across temperature, supply, process, and also across other situations. For the time being, let us assume this supply or this current source is independent of voltage. So it is constant across voltage. If it is constant across voltage, in that time we can say this ID2 and ID3 is also constant across voltage, because this ID2 and ID3 are derived from IREF only. Now the question is how we can generate this IREF. Okay. So a simplistic solution could be R1, means if you replace this IREF by R1, then we can generate a current IREF. But is it supply independent? Of course not, because we are deriving this IREF from VDD itself with the help of this R1. It means this current IREF is very much or strongly dependent on VDD. Now let us try to find out how much variation on I out when there is small change in the VDD. So let us try to find out delta I out by delta VDD. The derivation is pretty simple, so I have explained here. You can look at it. So ignoring ignoring R out, you can get this expression where you can see this I out is dependent on VDD, the amount of change in VDD, also R1 and the GM of the transistor M1, and also it depends on the ratio W by L ratio of M1 and M2. If you don't want to ignore R out, then also you can derive the same expressions, and this is the final I out by VD expression. Alright. Now let's go to cadence and simulate the circuit. So here, as you can see, I have terminated the output of the M2 transistor with a voltage source VDD. Here also in this case you can see we have a voltage VD over here. So what you can do, you can we have this expression that we have derived here, so you can use this expression, and you can use all these values. R1 is 500k, then you will get all the transistor parameter from here. Okay, so you can put all this parameter and you can verify from this equation that this delta I out or I out by VD is basically approximately equals, or it is equals to 12.29 microampere per volt. Now same thing that I am obtaining through the simulation, it is coming as around 11.92. So they are very close by, these two are very close by. Alright,